А ключ поставили мы? Ага, хорошо. Проверите, что мы в сети. Да, пошло, да? Ага. Ладно. Ага. So today we shall discuss rigidity theorem of maximal a tori for tori. So rigidity. Yeah. So теорема жесткости. Yeah. So this is about. So what we are going to prove actually is the following theorem that if you want to take the connected component of normalizer of, so if T is a diagonalizable subgroup, well. Yeah, better to say that actually it is already tori. So just T is tori. So it is isomorphic over the field K bar. So that means that we are considering now algebraically closed field for simplicity. Yeah, so that it is T is isomorphic to the product of the copies of multiplicative group in some power. So just if you are considering T, for example, as a subgroup somewhere, so in some GLV, then the normalizer of tori in G, the connected component of the normalizer in G is equal to connected component of the centralizer of the torus in G. So this is the set of elements of G such that GT, G inverse sits in T. And this is what centralizes torus. Yeah? So this is G and G such that G T commutes with E. Yeah? So this what we are going to prove, and in order to discuss it, so the last statement that. Yeah, so that we did that, and so
there is no way to conjugate
the element non-trivially. Yeah, so I mean there is a way. So let me just give you a basic example of. So counterexample. So it's not counterexample to the theorem, but it shows that the normalizer, of course, can be different from centralizer, but these connected components are the same. So it will be illustrative. Yeah.
Connected component of unity.
Yes. Yeah. So this the example is just GLNV. So here you take the maximal tori, which is diagonal matrices, and if you so this the form T1, Tn, where you just say that Ti's are not equal to 0, and so what is centralizer of this element? Yeah, so this if you start calculating it, so the centralizer of T with sufficiently general values actually, so with sufficiently general values Yeah, so you simply can do the following. So you can take the matrix, and so it is always convenient to compare the matrix. Yeah, so with T, G, T inverse. Yeah, so it is very easy to take the matrix explicitly and take the conjugate via the elements, and to write this expression explicitly and see that if your just TIs are so sufficiently general, simply means that TIs are not equal to the TG. Yeah? So you will see that the entries are multiplied when you do this conjugation. Yeah? So this you will see that the entries are just the diagonal entries will be the same of, I mean, if you compare here Aij here, the coefficients of this matrix and the coefficients of this matrix. So if so this is more or less will be written as Ti Tg inverse, maybe up to the sign, and this will imply that just if they're different, of course this entries cannot never be equal. So this means that centralizer of the element is equal to the centralizer of the torus and equal to the torus itself. Yeah? And if you have, so if you start thinking of normalizer, so the exercise is to show that normalizer of the tori. Yeah, so this is just the thing that makes, so it consists of two things, but it is, so this is somehow the changing basis up to the, so it is just permuting the basis. Yeah, so normalizer is generated by T. And permutation of the basis, and permutations of the basis. So, of course, we have only finite number of permutations of the basis here, so which is just full symmetric group of n elements. And this allows, first of all, to embed this, to have the some subgroup which embeds in this group in the normalizer, and it is finite. And then you have, so you extend it by T, so you have, you get the full normalizer. And the reason actually is that you for this, yes, so that this is again the question on eigenvalues. So if you, what you have, so if you have the element which looks like G, T, so here it is now convenient to take, so in order to commute it is convenient to compare G and TG, T inverse. In order to prove this exercise, it is convenient to look at the conjugation of T, so you know that it, so since it is in the normalizer, so since G is in the normalizer, the condition is that G belongs to, this should hold for any element T inside the torus, and if you assume that these elements are pairwise distinct, yeah, so this will show you that this will be more or less equivalent. So checking for such element, the normalization is just more or less equivalent to check that for the elements, and this actually tells you that the eigenvalue, so here this element is diagonal, so eigenvalues, you know that eigenvalues are not changed by the conjugations, so eigenvalue stays so of G, T, G inverse are the same, yeah, so this, noting that this should be diagonal matrix, so this means that this is diagonal matrix with the same eigenvalues, and this proves the exercise. Because the only thing that you can do with them is permute eigenvalues. So so this theorem shows that, of course, the more or less the connected components are the same here, and these connected components are just. But the group can be, the normalizer can be actually bigger. Also, it is clear that this doesn't happen. So this doesn't happen always. Yes, so it is not the case. Why? So why this can be not be true for arbitrary group? Yeah, I mean, if you have just the group G where you have this torus here, so you can multiply the group G by some unipotent subgroup. So definitely, I mean, if you have the torus here, so if it is in the center, so GU is center, commutes with G, so commutes with G and consists of unipotent elements. Yeah, so of course the centralizer of T will contain this GU, yeah, and this is the set of unipotent elements. It is clearly not the torus, yeah. So these are unipotent. So this is not the torus. So so the what we need for explaining this rigidity theorem. So let us recall the properties. So just recall from previous times that if you have D is a D group, then there exists some F, a finite group, such that D is obtained as the product of connected component and F. And this is done as follows. So you have the character of D. And note that so the characters are just yeah, so if you have the set of characters, so if you have two diagonal groups, yeah, so actually if you have any two groups, yeah, so you have the map of the corresponding functions, yeah, so the algebra functions. Yeah. So just and here you have the just the corresponding set of characters And you can reconstruct this algebra by generating this as a vector space by the characters. And here you have also the characters D1. And this set, so in order to understand, so for diagonal groups, it is easy to prove that just the set of characters, so characters correspond to invertible elements in elements of the algebra. Yeah. Of diagonal groups. Yeah, so it corresponds to the set of invertible elements here. So so this means that if you have invertible elements here, of course they map to invertible elements, so the characters map to the characters. And this tells you that, so the claim is that you have two categories. Yeah, so this D groups. Yeah, and also notice that you can also reconstruct the algebra. Yeah, so we can, given the set of characters, so we can reconstruct the algebra by the following. So if the different characters are always linear independent, yeah, so just different characters are linear independent. So note that if so, these are notice that these are finitely generated abelian groups. Yeah, so finitely generated abelian group. Yeah, because we have so as we have proved, so since we have the following embedding, so we have always embedding in some diagonal group of matrices, and this means you have the corresponding maps of surjective map of the algebra of functions to the algebra of functions of D. And characters here are unknown. Yes, so characters here, so characters are just known because they are just x. So this algebra is just the polynomial algebra of x and x inverse. Yeah. So you see that this is finitely generated. So the set of characters here is just, we described it explicitly, it is just the maps. So it corresponds to the integer numbers. And you just map the element with the coordinate x1, xn. So you map it to x1 and 1, etc. xn and, well, x I1, in. Yeah, so you are mapping the x and the corresponding powers. So this tells you that this group is Zn, and notice that so this algebra of functions should so this maps should be surjective, and notice that if you have So I claim that this map is also surjective on the characters. Yeah. So map is surjective on the characters. On characters. Yeah, just for yeah. So here we have just yeah. So here we discussed actually that what is the corresponding yeah, so what is the corresponding yeah, so what?
Is it a set of characters?
Chi is the set of characters of this group, yeah.
Why is it
Equal to Zn, because it is done explicitly, so that this is so this group is just yeah. So this group is just the product of GM in some power. Yeah, and if you look at this map to GM, you can think of this coordinate-wise. Yeah, so and coordinate-wise, it is just the map from GM to GM. Yeah, so the restriction of the corresponding subgroup. And this is just raising to the power I1.
so no other homomorphism from GM to GM is.
Yeah, so if you just solve the following problem for polynomials rings here, so the invertible elements are only t is so only powers of t from this point of view, and you see that they are precisely the characters here. So so for 1GM this exercise is very easy, and for proving that this is the full set of characters, you just have to restrict it to the subgroup of the form x1 times unit, etc. And then since the group is generated by this such subgroups, then of course the general character can look only like this. And yeah, so the only thing here is just this yeah, so here you have to just also to recall that yeah, so that the character here in this group, yeah, so this invertible element can be obtained as yeah. So let me put it as an exercise here, that the set on the set of characters this map is surjective. Yeah, so that this also gives you. So yeah. So let us put this as an exercise. Yeah. So we have discussed actually. So if so we already discussed that how to write down the set of equations for D. Yeah. So and this is the similar argument. So yeah. So this is precisely what I wanted to say, that. So this is finitely generated abelian group, and it is convenient to take the group algebra. Yeah. So the claim is that the algebra of functions is just the group algebra. So let it be denoted by k of chi of d2. Yeah. So this is group algebra for this abelian group. And this tells you that of course this means that since it is the subset and it generates D2, you have of course K of the maps between group algebra to this algebra. Yeah? So since this by assumptions characters are generated this as a linear subset, it is surjective, and since the characters are linearly independent, it is injective. Yeah? So injective. So this is since D2 is D group. And this is injective since the characters are different characters are linearly independent. Yeah? So this actually means that just if it is that of course it can happen. So here there is some observation that should be done, that that of course this map is homomorphism, and it can happen that some element maps to 0. But the element of chi of D2 is written as AI, as A alpha, where you have chi 1, I1. So you take the characters and you can you are taking the elements from this group and you are writing the polynomial that vanishes here. Yeah? So if you have f some polynomial, so if you have phi here, phi star. Yeah, so if you have the elements such that phi star of f vanish, then of course so you are forming some polynomial, but in the same time when you are writing down polynomial, it can be written as some, so this monomial in the characters is the character itself. So the element of f actually is written as some sum of characters with some coefficients. Yeah? So any element of this algebra is written as the linear combinations of the characters, and this means that just since they're different and linear independent, they should be all 0. Yeah? So since different and linearly independent. So and then since the different characters linearly independent, so this they equal to 0. Yeah, so this element equals to 0. So this shows that you have so you can reconstruct the algebras. So this shows that if you have the maps between characters, then you can recover the maps of the functions by taking corresponding group algebras, maps of group algebras. And this gives you the bijection, yes, so the categorical correspondence that D groups, so they correspond to the category of finitely generated abelian groups. And the correspondence is just here you have Holmes maps from D to GM, and to reconstruct it backwards you are doing the same thing. Yes, so you are just taking the homomorphisms of the characters to GM. Yeah, so, sorry, you are reconstructing the algebra of functions here, yeah? You are reconstructing it via saying that just taking the group algebra and considering this as the set of functions, yeah? So that taking, so this is finitely generated algebra. So, and then a finitely generated algebra gives you the corresponding affine variety. So, this is the correspondence. So here you, in this theorem, you can recover the corresponding characters. So if you have the character, so what we have discussed on previous class, that the characters of finite order vanish on connected component of D. Yeah, so this was done on previous class, and this was just noticing that the values of, if you have the character of finite order, so the set of values is the roots of unity. And this means that you map D to the finite set, which is impossible unless it is the map to the unit. Yeah, because already you have the unit inside the image. So this tells you that the characters, yeah, so this suggests that you can recover D0 via just, so you can take the characters, so this will be some free group plus finite group. So this is torsion group. Yeah, so let me write it down like torsion. And this set is defined canonically. So canonically, and this decomposition is of course up to the choice of basis to any element. Here you can add any element of the finite order, so this changes the basis of this group, but doesn't change how the decomposition look like. So these elements, so notice that we have proved that the subgroup is defined by the set of characters vanishing on this subgroup, and yes.
And you say that if the group is connected, then the torsion is zero.
Yes.
So could you please repeat how can we construct the group from finitely generated?
Yeah, so you take, you can take the group algebra. Yeah. So do you remember what it is? Yeah. So this group algebra plays a role as the algebra of functions on your group. It is finitely generated algebra, and you just take the corresponding algebraic variety, which is a group.
Why is it a group?
It is a check, and this follows because this is a Billian group algebra. So, in order to, so of course, what should be needed here is to write down the common. So just if you have the multiplication, so this means that so if you have so if you have the group, of course, so that you have this multiplication map and taking inverse, so you have you should have write down what does it mean. So how to write down this map. And the good exercise is to do it for GM. So to look how the product on GM is, and of course it is just, so for GM you are just, and this map of course corresponds to taking the corresponding multiplication on, so here you have two coordinates here, so like x and y, and you are evaluating it on x times y. Yeah? So it is this is saying that you are evaluating these elements on the set of these coordinates. So this means that the coordinate here maps to the corresponding coordinate here times the corresponding coordinate here. Yeah? So in order to say that when you substitute these values, they just and multiply them, so which is should be the converse map. So this will be precisely this element, and so you check that this is precisely, this gives you commutative group law. Yes. So so when you are looking at the characters, this noticing that the characters which are torsion elements should vanish on D0. So this means that D0 can be recovered. So is equal to the vanishing. So the set of chi of G equal to 1 for chi belongs to the torsion subgroup. And just if you have one inclusion is obvious. Yes, so you just take it to be d tilde, and you are taking. So you know that d0 sits in this d tilde because all characters which are torsions, so they vanish. And then you notice that this is actually the, so you do not add any, so if you have the element of finite order here, which is not in the connected, so if it has still some connected components, then you can go further. So this I do not want to stop on, and so you can reconstruct F not canonically via just saying that it is. So you take it the kernels of this free part. Yeah, so that chi belongs to Z key. So this is not this is not canonical group. Yeah, so not canonical. And also, yeah, so also you notice now that you have the corresponding product. Yeah, so that yeah, so what you know that this at least, so this group, if you look at this group, so you have the natural map from this product of these groups to D, so they have the same dimension. So you have, and of course, the thing is that you have to check that it is injective. So it is. So this map is. So this map is not injective. So this is only surjective map. Yes. So this is surjective. And it is surjective since it is the map of algebraic groups, and it is dominant. Yeah, so that we know that this is homomorphism. Of algebraic groups. Yeah, so that you know that the image is closed. So image is closed. And also, you know, that, to prove that it is surjective, it is sufficient to notice, to check that image is dense. Is dense. And this follows from just, so this is equivalent. So F, just if you have the map between algebraic varieties, so that affine ones. So that to check that, yeah, so here it is even, so to check that the closure, so they have the same closure for affine. So for affine, it is sufficient to check that you have so that KFY maps to KFX. This is inclusion. So otherwise, the check is that you have. So if x and y are not affine, so when x and y are not affine, you check that the same for rational functions. Yeah? So you check that k of y embeds in k of x. Yeah? And you know how the characters are mapped. Yes, so the characters are mapped precisely to this group and to this group. Yes, so that if you look at the corresponding characters of 2D0 and the characters on F. So since the characters here just so the characters of D0 can be identified with the K, and the characters of F can be identified with the torsion subgroup, and this tells you that just this set of characters. So this is just this is just the K. This is just this torsion subgroup, and you see that this is precisely so mapping component-wise. It is precisely inclusion. Uh-huh. Yeah, so нет, ну тут как бы про размер, нет, в смысле, нет, тут просто любой гомоморфизм, это просто как бы, это не относится к следующему, это просто сказал, что у них равная размерность, просто вспомнил, так сказать, чтобы у вас просто есть такой факт, что если у вас есть гомоморфизм алгебраических групп, то образ замкнут. Потому что образ конструктивен, а если ну, как бы, у вас подгруппа конструктивна, тогда она замкнута по Зарийскому.
То есть утверждение, что если одно...
Ну, утверждение, что чтобы доказать сериективность, достаточно доказывать следующее. Ну, вот первое, потому что образ замкнут, ну, как бы, вот, а второе, ну, как бы, значит, раз образ замкнут, достаточно показать, что он просто плотен. Это дает селективность. Ну, это просто, это тут, как бы, к слову пришлось. Ну да, поэтому как бы я просто сказал, что, ну, как бы, что ядро может быть, но это конечная группа, да. Ну, я просто для этого сказал, что ну раз гомоморфизм... для того, если у вас есть морфизм алгебраических многообразий, то, ну, если это морфизм афинных многообразий, то плотность следует из того, что алгебра функции y вкладывается в алгебру функции x. Ну а если у вас не афинное многообразие, то плотность можно проверять на афинных картах. То есть можно взять афинную карту здесь и афинную карту здесь. И все. Для этого, ну если уж у вас что-то плотно, то достаточно свести к этому случаю. А там дальше как бы плотность можно проверять на уровне рациональных функций, то есть что у вас вкладывается алгебра рациональных функций.
Почему вот это положение не изоморфизм? У нас же хер это тоже ZK плюс торс.
Не, потому что, ну, как бы ядро тут может быть.
Ну, как бы одно ZK плюс торс, другое ZK плюс торс.
Нет, ну, в смысле, здесь... Не, ну у вас, ну как бы, сейчас. Где-то мы все-таки к фактору переходим, вы знаете. Ну, то есть тут Yeah, so the question was that since I claimed that this is zk times torus, why this is not isomorphism? And if this is isomorphism, then you just I claimed that I claim that if it is isomorphism on the set of characters, this should be isomorphism of algebraic groups. So the reason is just that this projection, so this identity, so this is isomorphism to zk, but this could be just so here in this map to zk there could be inclusion in as the group of finite order, finite core. Ну, в смысле, что это вложение группы изоморфных ZK, но при этом не является изоморфизмом. Ну, то есть, как бы это вот, ну, в смысле, что yeah, so that the claim is that this map to just identification of this group and this ZK can be, from the viewpoint of this group, can be just inclusion of the group of finite covolume.
Why is it inclusion?
Ну, сейчас. Ну, давайте этот вопрос пока опустим. Давайте его потом прокомментируем. Я просто сейчас быстро не соображу. Okay, so then I want to speak about rigidity. Detailed is, I mean that just I denoted this subgroup of torsion elements. Yeah, so that vanish on the torsion subgroup as d tilde. Yeah. So maybe the problem is that just here you should have yeah, so that here you should still take the connected component, and so there should be the map to the subgroup of just a finite covolume here in precisely in this place. Yeah. But let me just postpone this. I just have to focus on this to answer. So what properties we shall need? So properties of the group. Yeah, so first of all, if you, yeah, so just let us put D and write it down as a product of finite group and the group which is connected. So connected. And the claim is that this D0 is just the torus. Yeah, so that claim that just if you have that just connected component, so D0 is isomorphic to GM, and the reason for this is that because of the characters of D0, so they just form the free group. Yeah? So this is, if you apply precisely the construction, then you get that D0 is just the product of the corresponding GMs. And this implies the following, that just you want to have so to ask the following questions, so to consider the following properties. Yes, so the set of elements of finite order in D is finite, of fixed finite order, yes, so just of bounded finite order in D is finite. Yeah, so this is just follows from the just you have the semi-direct product of D0. So you have a product of D0 and finite group. Yeah, so in order to consider the elements of finite order, yeah, so they look like the elements of finite order in a billion groups times something, so it is clear that they should be finite order in D, yeah, so that if you raise T, for example, to the power of F, so since it is commutative group, yeah, so since it is commutative, so this will be T1 times T2 in the power F, yeah. So this will be identity element because it is just the order of this finite group, and this will be the element of should be the element of finite order. So this it is the element in D0 of finite order. So we have reduced it to connected component, and this connected component is just the product of copies to GMs of GM, so it reduces the question to the single GM, and in GM you have clearly this elements of finite order in GM is finite bounded order are just roots of unity. Yes, so just in GM reduces to just to the group GM, and here these are roots of unity. Roots of unity. Unity of bounded order. And this is of course bounded set for one GM because it is just the solution of polynomial. So in GM it is just the solution of polynomial psi times n equal to 1. Okay? So and the second important claim for us that the elements of finite order are just there are quite many of them. They are dense in so here you have bounded order of this set, but if you take all the torsion elements, so torsion elements are dense, in D. Zariski dense, yeah. And again, this follows because the roots of unity are dense in G. Yeah, so since roots of unity for just n goes to 0 are dense in G. And here, of course, we use that the field is algebraically closed. Yeah. So here you are using that k is equal to k bar, so extracting roots of unity gives you just infinite number of elements, and for one dimensional space it is sufficient to prove to establish that it is zeroisly closed. Yeah? And also notice that so here you have the correspondence between the groups and the characters. Yes, so if you have if your field is non-algebraically closed, this correspondence also works, but there is additional Galois action, and just if k is not equal to k bar, so this you have also Galois action, so we have also Galois action. On the set. I mean, if you have the homomorphism of the groups, which is defined over your given field K, so just defined over K. So this gives you the map of abelian groups, so the correspondence is just the maps of abelian groups. With the corresponding Galois action, yes, so with just which is consistent with Galois action, yes, so that if you have the chi, yes, so that just then if you just have some phi which sigma that in the Galois group automorphism of the field of k bar over k, yes, so then the character you can just twist the value of the character by sigma, and this maps to just the image of just 5 sigma is just sigma of 5 chi. Yeah? Yeah, so the thing is that when you are thinking of characters, you are mapping it to the field K, so you are acting, yeah, so just yeah, so this makes these things as, yeah, so this can be viewed as, notice that you are considering homes from D to K, and so here the Galois group acts trivially because it is the precisely, so just so here you may think, so when you're thinking of this homomorphisms, yeah, so then you can do the following, so you can twist the character, yeah, so you just you can take the character and twist the value of the character, yeah, so you are just evaluating it at point, and just if you substitute the just you can take this evaluation and just so you consider the homes just not in K, so not all homomorphisms, yeah, but you are considering homomorphisms in K bar, yeah. So this tells you that, I mean, if you had the picture that you have taken the homomorphisms in K which are defined, so homomorphisms you are considering here, they are over K bar, yeah, so just, so this means that you are not picking precisely the structure that, so the homomorphism shouldn't preserve the structure of the group, thinking of this as a group over K. And this tells you that you can twist the homomorphism by the character, so by twisting the value of this character, because actually it is the maps from D to K bar. And this allows, so this gives you the action. And of course the character is defined, the character becomes the character over D to K if it is fixed by the Galois group. So that's the reason why we're introducing the action like this. So if character is fixed by the Galois group. So you should think of this set of characters as the characters over K bar. Yeah, so the characters are considered over K bar, and this gives you the abelian. So these are abelian groups with the action of Galois group, and the correspondence between the maps here and here are just that phi should be the map of the map of Galois modules. Yeah, so that in the correspondence that phi is the map of homomorphism of Galois representations of Galois representations. So it should commute with Galois action. And this is a more general correspondence that should be done if you want to remember the structure of your group, how it is written in the equations over the field K.
What was the corollary? If I plus I sigma.
Но это в смысле, что чтобы проверить, что у вас гомоморфизм из D попадает в K, вы просто применяете, для любого элемента. Нет, имеется в виду, что, что вообще мы все характеры, да, рассматриваем как гомоморфизмы в группу над K с чертой. Как бы вы можете у таких гомоморфизмов есть естественное действие. Просто вот эта группа, если она определена над K, и вы берете ее K точки, например, да, то вы применяете автоморфизм группы Galois, он ничего не меняет, потому что у точек координаты в K маленьком. Но чтобы у вас возникло действие группы Galois, надо отображаться в K с чертой. И теперь вы можете спросить, а какие гомоморфизмы определены над K? Те, которые сохраняются, да, группы Galois. Все хорошо, да? Yeah, and now, so you have these two properties. Yes, so the one is the set of elements of finite order is bounded finite order is finite, and then that the torsion elements are dense. So now let us put.
Как мы редуцировали D0 к GM?
D0 просто потому что характеры D0 это свободная группа. И вот из того, что это свободная группа, мы можем взять групповую алгебру и увидеть, что это GM. То есть, если у вас есть группа характеров свободная группа, то групповая алгебра восстанавливает алгебру функций, которая является просто полиномиальной алгеброй от x с минус 1. Это дает то, что это степень GM. Поэтому нам пришлось тут поговорить, не совсем удачно, но это я поправлю в следующий раз. So rigidity theorem will be formulated in a little bit more complicated way, but actually it is And so how we will formulate it, it is just convenient for the proof. Yes, so suppose you have V is the variety, which is just connected, well, irreducible, algebraic variety. So you have just assume that we have a map. So G and H are algebraic groups. So assume that we have that phi is the map from V to G to H. It is some. So this is some well, homomorphism of algebraic varieties, of morphism of algebraic varieties, of algebraic varieties. And suppose we have the following property that first of all, so property for G. Yeah, so so in G, so this is one of the properties that we have for diagonal group. In G, elements of finite order form as a risky dense subset. Yes, for H, we shall assume the first claim that we just in H, the set of elements of bounded order is finite. Set of elements of bounded order is finite.
Bounded order is any bound.
For any bound, just yeah. So for a fixed bound, yeah. So as just of order less or equal than n for fixed n is finite. Yeah.
In this case, you can choose fixed n equal to
For any fixed n. I mean, you choose the number. I say that the number of elements is finite. I mean, of course, it can happen that the group has just an infinite number of elements of finite order, yeah? Of bounded finite order. This also happens. So for any fixed n is finite. So actually, this is a property of abelian groups, just for the reason that, so let me make these remarks, that this works even in more general setting than the groups we're discussing here. Yeah, so just assume that, so fix n, and you may just suppose A is a abelian algebraic group. You may do the following. So you may take A and mapped to itself. So you can consider the following homomorphism, yes, so that you can have the following additive notation. So you add the x, so you take a point and you can add it n times. Yeah?
Is 1 and 2 the conditions or the...
These are conditions, yes, so these are conditions. So maybe let me finish formulation for the proposition, and also that, yeah, so also assume yeah, so first of all, for G, you are just saying that we have many elements of finite order, so such that it is the risky dense in G. For example, if you take unipotent group here, it's not the case. Yeah? So in unipotent group, you cannot have many elements. Or at least over algebraically of the field of characteristic 0. Yeah? So the second is that you just each element of finite order is just the set of elements is finite. And the third tells you that this phi is a family of homomorphisms. So phi is a family of homomorphisms. So meaning that just if you have a point x inside V, then 5x G, yeah, so if you have, this is homomorphism from G to H. Yeah. So if you look at the function with respect to this of algebraic groups, of algebraic groups. But here you just this is automatically plugged in the condition because it will be a morphism, and if you yes, it's not automatical, yeah, because you should have the product structure, yeah, so the product structure should be should be algebraic, yeah. So this then the claim is that then phi is just constant, yeah. So then just 5x is equal to 5x0 for some x0 in V. Yeah, so for some x0 in V. Yeah, so this so phi is constant. It doesn't. So what is the theorem about? You have a family of homomorphisms of algebraic groups parameterized by the variety V. So the claim is that so this set is so if you have these two properties, then actually this family is constant. Yeah. Yes, all phi's are the same map. Yes, or maybe just I would say just like this. Yes, so just all phi's for all. So this happens for all x. Yes, so for phi from G to H. Yeah. So let us look what happens here. And so the proof is easier than it is formulated, actually. Yeah? So but it is quite important technical part of this life. Yeah. So first, notice that if you look, so fix some point. Yeah. So just fix some point of V, and look at the. So here you have F torsion. The finite set of points, so elements of finite order. So you may look at what is just you may take this set and look how it so fix some point x on V. And look where do we map the torsion elements. Yeah? And of course we map this set of torsion elements inside in the torsion elements of H. Yeah? Because it is homomorphism. Yeah? But notice, so this, since it is algebraic, this implies that phi of x, because you know that the risky closure of this is just G. So this we know that this image sits in the torsion set of H. Ну, потому что это алгебраический гомоморфизм, да, что, что вот эти предельные точки.
Первое, да, то есть torsion, все крутящиеся точки замкнуты, а значит...
Да. Ну, вот я написал. Yeah, so because if you pass to the limit, yeah, so then you will have, the inclusion will remain the same. Нет, оно у нас, в смысле оно будет, оно плотно, оно как бы, оно никогда не может быть замкнутым, да, но ну, например, для Тора, но вот это и это можно положить Тором, поэтому она никогда не будет замкнута. Да. Okay, but notice that... Не, в смысле откуда? Не, ну, в смысле... Не, вы сказали замкнутые, за риски замкнуты, вы имеете в виду или что?
Ну, откуда берется вот это следствие?
Про что? Это потому что фигоморфизм, точка конечного. Yes, so this is, вот это или вот это вы имеете? Вот это, ну потому что если фи непрерывная, из-за того, что что вот это множество получено как замыкание, то у вас сохраняется включение. Ну, в смысле непрерывность фи. Замкнутость кого? Ну, в смысле замкнутость по зарискому, что вот замыкание, ну, в смысле, что если у вас есть включение фи от x, ну, если у вас есть морфизм, so if you have, so this is a general statement of the following type. So if you have, suppose you have the morphism of from x of y of algebraic varieties. So here you have z is a dense subset. Yeah, so this is dense, the risky dense, meaning that the closure is equal to x. And then I claim that f of z is just so if you have the equality that the inclusion of f of z You say just. Just a second. Yeah, so this is sorry. This is not I want not that I wanted to say. Yeah. So you have homomorphism. Yeah, so that the torsion points, yeah, so they map in the torsion points, yeah, but then just sorry. Then we can ask the following. So what is? So if you have, so let us fix the element from here. Yeah. So this element is of finite order, bounded order. Then we just have the 5x of y goes to so if this order is n, so then you are mapping to n torsion points of H, so n torsion points of H. And this is finite set. Yeah, so then you can think of just we can vary this parameter, and this gives you that you have the map from f of v. So when you fix when you fix y, yeah, so we fix this y, and this goes to this finite subset. Yeah. This tells you that this since v is irreducible, so since v is irreducible, then this implies that this is just a map to the point that so phi of v y is a map to the point, and doesn't depend on, so you map v to the finite set, so you map it to the point, and this doesn't depend on v. Yeah. Then you can do the trick. Yeah, so you just yeah, so you can yeah, so you can write down this condition just as follows. So you can fix this whole so this means that you have the following property. So if you take this x and y and you are taking x tilde y, so we have proved that this holds for any x and x tilde inside V, and y is the element of finite order. Yeah? Okay, so you have this kind of property for any x and x tilde and for any y torsion. And now there is a small trick, because so this we want to reformulate this condition in terms of that, we want to have the following property, that we want to use the following property if you have x and it is a map to somewhere. So if here you have Z is a dense, Zariski dense subset, if you have f of z is the map to the point, then the map of all x is the map to this point. Yeah? So precisely what you said, the point is closed. Yeah? So you just since the just point is closed. Yeah? Yeah, so if you have just the...
Does the point depend on the order of y?
I mean, this one doesn't. I mean, if you know that f of z is the map to the point, then f of x is the map to the point. And of course, if x, this thing would have a ride, so we cannot say anything. But this can be reformulated. You are constructing the different family of homomorphisms. Yeah? So you can construct the new map. And this map is just constructed as follows. You just take, so on x and so for psi on x and elements of g, so on y, yeah? Just let me... Yeah, so 5 on x and g is defined as taking phi, and you may multiply by the inverse for some fixed point. Yeah? So we fix x tilde and multiply like this in the group. Yeah, so this is inverse in H. And this will be, since you have this property for all torsion elements, this implies that this is just, so this map is the map to identity. So this implies that psi of x g is the map of identity for any g that is the element of G torsion. Yeah, I have just, so this was just equality for G from G torsion, but any 2 points of X. And then I have rewritten it because I'm able to just outside of this, I cannot say anything. But you are working in the group, so I can just invert this one, and you get that this equality just becomes that this guy is just identity element in H. And this implies that psi of x g is equal to E, since G is equal to the closure of G тоже. Okay? So this shows the rigidity lemma. Согласны теперь? Спасибо. Yeah, so maybe it is a...
Why is this proposition equal to rigidity that was stated?
Yeah, sure. Just let me apply it. So, yeah, so let me... Yeah, so just proof of rigidity theorem of rigidity for tori. So first, just we put yes, so D equal to H equal to G. Yeah, so notice actually that we never used that this was homomorphism of algebraic groups. Yeah, so we just use that the torsion elements map to the torsion elements. So we can erase this. Yeah. Okay, and so put it like this, and for V, you just you want to prove that actually, so on given the element from the normalizer, of course you have the map from D into D, so which is the conjugation. Yes, so X maps to X n n minus 1. So this is a family of homomorphism. So we apply our theorem to V equal to the connected component of the normalizer, and this our theorem gives you the family. So this map, yeah, so gives you the family of the maps from the connected component of normalizer times D to D. Actually, it gives you the family of the map of the normalizer times D to D, but you apply it to connected component. And this tells you that this phi is that doesn't depend on, so does not depend on n in the normalizer. So you can put it n to be trivial element. So this means that phi of n x is equal to phi of trivial element x, and this is just identity map x. So this means that you are considering the elements that centralize x. So this is just a direct consequence, but this is quite important theorem for the studies. So let me make a break, and then we can discuss the next big topic about just structure theory of the structure of solvable groups. So this is quite important part, and will be quite technical. Okay. Yeah, so now I want to make a slight comment about that problem that arose in proving theorem. So. Yeah, so we wanted to discuss the character of diagonal group, which were just, so that was z to some power, and the finite group, yeah, just some finite group, some torsion group, yeah. And notice, yeah, so if just, yeah, so note that you have inclusion, so D0 is connected component, so you have inclusion as a closed subset of D0 and D. This tells you that chi of D suggests, yeah, to the group of characters of D0. So what can be said about these groups? So notice that there is a notion of dimension. So we know that, of course, the dimension of D0 is equal to dimension of D. And in the same time, it is transcendence degree of the algebra of functions. Yes, so transcendence degree of the algebra of functions on k of d over k. And now you have to do the following calculation. Notice that torsion elements are the elements of finite order, so they do not affect so they are always algebraic. So this means that if you look at, so since k of d is the group algebra of the group of the characters, so notice that this group algebra decomposes as the product. Well, and this as the product of group algebras, and notice that this is so this is algebraic, and only this has transcendence degree. Yes, so here you have all elements. So here all elements are algebraic. Yeah, algebraic. Yeah, because if you have the element of finite order, so g to the power n is equal to e. Yeah, so this is just algebraic equation. Yeah, so algebraic equation. So just polynomial equation t to the power n equal to e. So this is the set of algebraic elements. So the transcendence, so dimension of d is just transcendence degree of this algebra, and this is precisely polynomial algebra. Yeah, so this is just polynomial algebra. Transcendence degree of k of z, which is just n. So this tells you that out of this just out of this decomposition, you can read off the dimension. And this tells you that if you look at the characters of D0, yeah, so that this tells you that just the characters of D0 is just should be z to the same power since dimensions dimensions are equal, yeah. So a priori there could be some torsion, yeah, here, but notice that we proved that for connected group there is no torsion, yeah. So for just for connected group torsion is equal to 1. So you see that chi of D is just either from looking at that you have the corresponding embedding, and so at least you see that this this group is a group of characters is isomorphic to z to the power n. Yeah, so this is zn times torsion, and this is surjective mapped from z to the power n. And then you consider, you want to consider the corresponding splitting. And this splitting this is just the choice of z to the power n maps here via some basis. Yeah, so just and this gives you gives this splitting on the set of characters gives you the map in the inverse direction, so gives you the map from D to D0, and this is yeah. So since this splitting is just injective map, yeah, so which is of course injective, then so this gives you homomorphism here, which is surjective, and this gives you a finite group as the kernel of this homomorphism, for example. So define finite group as the kernel, and since so this will be finite because they have the same dimension, yeah. So kernel is finite since just phi is homomorphism of groups of the same dimension. And as in the definition, I have defined the tilde, and I have written it in the right way on the blackboard that the zero set of z to the power n can be the group. Yeah, so but it contains the connected component, but it can happen that there are also some other connected components. So that's why the kernel of the torsion group. So that's why you have to get rid of them as well. Okay. So, and the map that I considered, it was more or less this inclusion of, it was the map of this part into this group of finite index, as we have the map here. So that's why that was, that argument is not the most convenient for the proof, I would say. Yeah, so, and now I want to recall the, now I want to discuss the following program that we are going to do. So, just suppose you have G, which is a solvable group. Yeah, so it is just, so you are studying commutants, and so the just commutant of the commutant, etc. And then it should be equal to identity. Yeah? Unit element. No. It is the group that you start with G. Yeah, so the group which is those elements can be written as commutator. So it is opposite, precisely opposite story. For example, SLN. Yeah, for SLN, any element is written as the commutator, product of commutators of small. And here it is opposite story. So this is, so you are considering series of commutators, so the corresponding series is GI, which is GI minus 1, GI minus 1. Yeah? And this series terminate, so it can happen that they stabilize, but they do not just, the group is called solvable if you stop it. So we have, so if it is algebraic and solvable, we have noticed that it can be put to the set of triangular matrices. And the triangular matrices we denoted by T and V. Here either Tk or just Tv, where this is some vector space. Yeah? So and here you have the set. So for triangular matrices. So here you have, here you can explicitly write down, so here you have the group which is, consists of the matrices, of unipotent matrices, and precisely you see that if you have triangular matrices on V, the set of unipotent elements for these guys are precisely, so these matrices are denoted by U of V. So this set of unipotent elements is equal to UV. So this is a direct check. Yeah? So you have to take this matrix and understand when this matrix can be unipotent. Yeah? And you see that, first of all, so this means that it doesn't have eigenvectors or the corresponding eigenvalues which are distant from 1, so you get that it should be written in this form. And now what is the benefit? So we have put just if G is solvable, then you can, so for, and here also you have, in this group you have natural torus, so which is the set of diagonal matrices. So you have exact sequence as you have the group of triangular matrices. You have the group of unipotent matrices, and you can also take the triangular matrices, factorize it by the set of unipotent matrices, and get that only what is essential only the set of diagonal elements. So you get as the quotient the torus. Yeah?
It's exact sequence?
Yeah, so this is exact sequence. So maybe I shall put it as an exercise, but more or less I explained. And also this exact sequence has the following property that I'm looking at this torus also as a subgroup. Yes, so I can look at this maximum. So this torus can be thought as the quotient, this entries of diagonal. So this is precisely, this map is very easy from algebraic point of view. So this is just taking the matrix from lambda 1, lambda n, and taking just the eigenvalues or the corresponding eigenvalues. Yeah? So just taking projection to this part of the matrix. And of course, what maps to the unit is precisely the matrix of this form. Yeah? So, and also, of course, there is, so here you have, this torus can be embedded in this group of triangular matrices. And if G is solvable, then you can put G inside the set of triangular matrices. And of course, if you want to discuss unipotent elements in this group, so this is a set of unipotent elements, which is just, which is equal to G intersection with U of V, and it formed the group. Yeah, so form the group. So here, if you take G, take the set of unipotent elements, then so you can restrict this homomorphism pi to G. So you have the image of pi of G, and of course it is it will be now the subgroup of diagonal group, and this will consist of semi-simple elements. Yeah, so just consists of semi-simple elements just because they are subset of diagonal elements. It is an algebraic group which is the closed subgroup of diagonal group. Yeah. So actually, if you want G to be connected, yeah, so if G is connected, then P of G is connected. And we have derived that it is just a torus. Yeah? So it is just some GM in some power K. So here you have this corresponding splitting, but it is not clear if, of course, if you take this pi, it is not clear that after the splitting, so this splitting is not consistent with this diagram. So the question is the existence of the splitting of S. And this will be the main point for maybe this class and the next class, because it will be a rather technically involved story. So the question that we want to address is to
So in field G not necessary, are not necessary semi-simple elements.
P of D.
Field G.
P of G is necessary the set of semi-simple elements here. So, but it is the subset of the quotient group. Yeah, so of course you can take these elements and embed them backwards to the triangular matrices, but it's not clear that they will be just still in G. Yeah? Ну, то есть, как бы, конечно, мы взяли G, ее отобразили как фактор на множество диагональных матриц, но просто это, тут даже, как бы, дело не в том, что даже что вот эта диагональная матрица, это просто набор собственных значений, я как бы образно написал, да, потому что, ну, вот это отображение, оно сопоставляет матрицы и ее собственные значения. Ну, как бы вы здесь, конечно, утверждается, что вы можете эту матрицу снова вложить сюда, да, то есть это расщепление. Но если вы даже возьмете G, ее отправите сюда, здесь-то они, конечно, эти элементы будут полупростыми, ну, просто это набор собственных значений. Но когда вы ее поднимете сюда, вы не попадете в G априори, без каких-либо требований. Вот как бы то, чем мы будем заниматься, это доказывать, что вот это S существует. So, just, для любого же, да. Ну, да, разрешимого. So, program and that there exists the splitting the section, a section S from P of G to G that just splits the exact sequence. Yeah? So splits.
You mean it's divide all the
Yeah. So, morphism of algebraic groups. Yeah, so actually, yeah, so it is just our aim is to find subtorus here. Yeah, so just aim to find, GM in some power k in G. Yeah, so such inclusion. So that was one of the reasons we would we won't use rigidity here. I mean, in this statement, this will be a little bit proved a little bit differently, but it will now be some long story that to which we are just heading. Yeah. So the problem is that you cannot just do it at once, so we shall do it just not very fast. Yeah. So just okay. So let us start with that, and notice that what are just of course, if you do not have any semi-simple elements, then you are done. You are nothing to do. So the idea, if you have non-unipotent elements, so start with X in G, non-unipotent elements. And any non-unipotent elements gives you automatically semi-simple, yeah, because you have Jordan decomposition that we established. And then it means that you have a semi-simple element. non-trivial semi-simple element. Then I want to study orbits of semi-simple elements. Study orbits, so study orbits of semi-simple elements. Under the action of some group normalizing this element. Yes, so that just let us consider the following story. So yeah, and in the end of the day, yes, so we shall start studying. Yeah, so we shall discuss how to study these orbits, what are the properties of these orbits, and we shall be just invoking more and more geometric information, and then I will prove this statement by induction to nilpotent groups and just the study of the properties of nilpotent groups. Yeah, so actually notice that in this exact sequence, so this group is solvable, and this is nilpotent actually. This is nilpotent as the subgroup, because you can take the corresponding commutators, and so here you are taking always the commutator with the subsequent series of commutators with itself, and here you are taking the commutator with the group itself, and this decreases the size of the group. So let us study the orbits of semi-simple elements. So suppose you have the following story. So S sits in some GLV that in some linear group that we put to be G, and H normalizes S. Yeah? So normalize S. Sorry, and the S normalizes H. Yeah. So and assume that S normalizes H. So just what we're interested in studying, just we can take S and yeah, H is just some subgroup of G, algebraic subgroup. So suppose this element normalizes this subgroup H. So I want to study, you want to start studying the orbits of semi-simple elements. Yeah, so meaning, of course, so let this. Yeah, so you want to start studying orbits, for example, in G. So in G you can study GS, G inverse, but there is some bad point about this map, because if you take the unit element, yes, so this will just if so if you so you want to consider the tangent space of the orbit in S. So by this I denote to the orbit, and this is tangent space. Actually, this is the only place that you really need Lie algebras in our picture. So everything except this part that we're going to discuss more or less today and next time can be done without referring to Lie algebras, and it is very good point somehow. And only this one, it is this is the place where it is very hard to avoid Lie algebras. So you want to consider this. You want to consider the map from the tangent space of the group. So the problem is about this thing that this is so this tangent space, tangent space to the orbit sits in the tangent space to the group, but in the element of S. Yeah. So you want to make a shift such that, and we had the Lie algebra, which was the tangent space in the unit. So you want to move everything to the Lie algebra, and notice that instead of this variety, we can consider G as G inverse S inverse. So this is also subset of G, and for example the property of this varieties are more or less the same as this one. If this is closed, then this is closed, because this is just translation by fixed elements. Yes, so they have more or less the same properties. So that's why we will be first studying this kind of variety, and what is the benefit? Yes, so the benefit that here this variety contains unit. Yes, so when G is equal to 1, yes, so you have unit here, so you can consider the tangent space of this variety G as G inverse S inverse. Yeah, so let us say that it is gamma of gamma S, for example. The map from S G to G. So that maps G to G S G inverse S inverse. And notice that so you can take tangent space of gamma S, and this tangent space. This tangent space in E of image of gamma S is obtained as it is obtained as the just image of the tangent space of G. So just you can consider the corresponding differential. So notice that of course this part is somehow is a joint action. So yeah, sure. Mm-hmm.
So I could come to the next class with some break.
Что?
Сейчас 14:22,
А, давайте закончим. Да, давайте. Да, и единственное, да, что я скажу. Yeah, so let me say one moment about this condition. So why we just wanted this condition. If you want to, so if your group H is normalized by S, notice that if you write down H as H inverse S inverse, so notice that you can look at this element that belongs to H, and this is an element of H. So it is also, so this S it can happen that S is not an H, but this subset will be inside H. Yeah, so it and we can finish. Happen that S is not in H, but gamma S of H sits inside H. So this is the second argument why we want to study this variety, and so next time we shall discuss, for example, that the orbit of semi-simple element is closed. So that will, and this map will be helpful.